Okay, so we're going to continue with a note today, and then tomorrow I'll provide you with a little assignment just to review some of these concepts and see how your understanding is. So, what I would do with this is I will provide you a PDF with this file. I would just print it off, and then you have your note, you can write on it, highlight things. I think that'll be easier than trying to draw all this stuff. So, which I think when I'm in class, I provide you with a handout anyway. So here is a really nicely labeled diagram of a neuron. So it shows the dendrites. Remember, we're talking about signals here. So if you recall your dendrites, the signals move through the dendrites. So always into the dendrites, through the cell body, down through the axon, and out the axon terminals. That is the direction, and the direction is important. So your dendrites, as it states here, are your receivers. The axon terminals are the transmitters. So they are either going to end, there's three options here for where an axon terminal will end. So it's either going to end up in a muscle, which will contract. It's going to end in a gland, which will release chemicals, and depends, they could be hormones. Or it's going to end at another neuron. And in that case, we're going to get something called a synapse, which we're going to cover later. So there's your three options for your axon terminal. If you recall from yesterday, we talked about Schwann cells. In this case, when we find them on the axon, they make myelin. And myelin is a lipid. Okay? And the myelin is important for certain types of neurons. Not all neurons are what we call myelinated, but the ones that require signals to move through quickly are. So in this case, they will insulate the axon, keep the signal from jumping from one neuron to another. So people who have MS, multiple sclerosis, their myelin, those fatty cells that cover the axon, actually that the fatty part starts to degrade, and sometimes it causes the signals, the electrical current, to jump from one neuron to another, or just stop altogether. So, and that is what causes the symptoms of MS. They have trouble a lot of times with movement, walking. They can lose sensation in their limbs. And that's because that for some reason their body is attacking that layer like it's foreign. So there's all the parts of the neuron again, and as I stated before, direction is everything with neurons. Okay, so incoming signal to outgoing signal. So the electrical nature of nerves. There are three factors that contribute to maintaining a resting membrane potential. So that if we remember back to that note we did where you filled in the blanks, it was a general overview. It talked about resting membrane potential. So when you have a neuron, there is a voltage that is maintained inside that neuron at all times unless the neuron is conducting electricity. So your neurons sit at a voltage of about negative 70 millivolts. So the inside of the neuron, that's what its voltage is. And there's three things that allow that voltage to be maintained at all times. First of all, so again, when we go to the next diagram, it might help you understand. But first, there are large negatively charged proteins in the cytoplasm inside the axon. So when we look at the axon here, if you look up here, there are these large proteins that are in there that have a negative charge, and that contributes to that negative 70 millivolts. Sodium cannot move through the ion channels into the cell very easily when the cell is not actively conducting electricity. But potassium moves outside easily. This ensures that there's more sodium outside the cell than inside at resting potential. So if you look here, I'll blow this up, notice that sodium is positively charged and so is potassium. So if there is a lot of sodium on the outside, there's going to be a higher positive charge outside than inside. Okay? And potassium can also move freely through. Now, the sodium can't really get in easily. So where it can't get in where it's negative, you would think it would be attracted to the negative because negative and positive attract. And yes, that's true, but it can't make its way through the channels. Remember, back to our very first unit, we talked about channels, how things move in and out of cells, and this is a cell. So these channels can open and close and be regulated. So typically when the cell is at rest, the sodium can't make it through the channel. And remember, the sodium needs a channel because it's charged. We have that phospholipid bilayer. If you recall, charged ions don't move in and out easily. So the channels that allow sodium in are kind of closed up when it's resting, but the potassium ones are not. So the potassium can move out. So we just get an overall larger positive charge on the outside of the neuron than the inside. Also, we have something called the sodium potassium ATP pump. And the term ATP means this pump works using energy. And remember, pumping things against their concentration gradient requires energy. And a lot of the energy that we require when we eat our food actually is used just to pump things against concentration gradients. And you may remember that as being a fact when we talked about cellular respiration and the ETC and maintaining a concentration gradient of hydrogen ions that required energy. So here we have a pump that actively transports sodium and potassium ions in ratios that leave the inside negatively charged. So it pumps 3 sodiums out for 2 potassiums in, which means we're maintaining more positive on the outside than the inside. And that all contributes to that magical number of negative 70 millivolts, which is the voltage inside the neuron when it is not conducting energy. So when it's just hanging out. Conducting electricity, not energy. So just some terminology. The process of generating a resting potential is called polarization. So what happens is when it is sitting at negative 70, it is polarized. And obviously it goes away from negative 70 when we conduct electricity through there, and then it has to go back to negative 70. So the process of going back to its norm, which is negative 70, is called polarization. So any cell with some separation of charge on either side of a membrane is polarized. Okay, so we have differences in charge inside the cell and outside. So if we're going to then take that neuron and take it from its resting negative 70 millivolts and actually conduct electricity through it, that process is called depolarization, which means we have to move away from the negative 70 millivolts. So that is required to move an electrical impulse down the axon. Depolarization, this is important, is caused by a stimulus. So how do we get that? That's nice. We're just going to let that phone go and I'll turn it off and go to message. There we go. Oh no. There we go. Okay. So we're just going to let that depolarization go. And that happens because of these sensory receptors on your sensory neurons. So the question is, how do we get the electricity to start? How does light cause electricity to start moving through the neuron in your eye? How does pressure, if you push down on your finger, so if you just take your index finger and press down on something, you are feeling that. And the reason you're feeling that is your pressure receptor in your fingertip started electricity to be conducted down that neuron, and it went all the way to your brain. So you conduct electricity from your fingertip to your brain, so your brain could feel or perceive that pressure. Okay. And so, how does a sensory receptor do that? How does pressing cause electricity to be conducted through these cells? How does light cause an electrical signal to be moved through the cells? How does any sensory receptor cause electricity to be moved? And that is the question. And it doesn't matter what type of receptor we're talking about, whether it's a response to light or chemicals in your nose, on your tongue, pressure, pain, they all start conducting electricity the exact same way. Okay, so all those different receptors start the same process of conducting electricity, which we're going to look at. So I will link, there's two links here that aren't going to work in a PDF. So what I will do is I will add those two links so you can check them out. I'll add them to your lesson today. They're just nice little animations you can take a look at. So we have what is called an electrochemical gradient, how information flows through electrons. So we know direction. This is just, the direction is so important. We're going to conduct electricity like this, in that direction. And how it's done is we need to change the voltage. So again, if we look at what I've done here, or what my idea, I think, at this point was I'm showing you a piece of this axon. Okay, so you have this diagram. Just, show a piece and bring it down. So this is just showing what's going on in that one section of the neuron. It's going on in every section of the neuron, but we're blowing up one section. So what you need, where are all these positives? These are all your sodium ions that are on the outside. Okay, we also have some potassium ions on the outside. And this negative is on the inside, is large proteins that are charged negatively. And of course, the concentration on the outside is, so this statement right here, there's more positive charge outside the membrane than inside. Hence, we have potential energy. Remember, a difference in charges gives us potential energy. So just a little reminder. And the positive charges on the outside are formed by the sodium ions mostly, and some potassium ions. And the negative charges inside, in the cytoplasm of the cell, there's some large negatively charged proteins. Okay? So, take a deep breath. Okay, so what is important here is that we're going to relate everything to this graph, and you will see this graph again, so you do need to understand what's going on this graph. So what we have, there's a lot going on here, and I just want, just to do a general overview using this picture, because as far as difficulty in understanding a concept, this one tends to throw people a bit. The rest of the concepts we learn this unit are, they're much easier to get your head around. The action potential, how electricity is moved through the neuron, can be difficult for some people. So here, again, is just a blow up of what this is. Okay, so we're just, we're just moving down in this section, and we're looking at the membrane and its channels and what is going on. So we know at rest we have more sodium on the outside. So you can see here, more sodium on the outside than the inside. And we are sitting at negative 70 millivolts, which is shown right here. Okay, So that's, the graph is showing the voltage at rest. So if we want to move electricity through this neuron, we need to change the voltage, okay? So to change the voltage, we need, the first thing you're going to do, and let's write it up here. So you just want to remember, to change voltage, we need to open sodium channels. So step one in conducting electricity. Step one in conducting electricity. Open the sodium channels. Electricity. Okay, open sodium channels. Okay, so when I talked about how does light in your eye cause electricity to be conducted to your brain? How does pressing on your finger cause electricity to be conducted to your brain? How does chemicals cause electricity to be conducted to your brain? All of those sensory neurons, all of those different things, whether it's pressure, light, chemicals, sound, they all do the same thing. They all open sodium channels in the neuron at the dendrite. Okay, opening sodium channels changes the voltage, and that's what we need to do to conduct electricity. So step one, all your senses, all your sensory neurons, whether internal or external, when they are triggered, they open sodium channels. The trigger might be different, but the trigger will always open sodium channels. Excuse me. So when sodium channels open, so step one, open sodium channels. So what happens is, as soon as some sodium channels open, this sodium starts flowing in. And as soon as positive charge starts flowing in, the charge overall on the inside becomes less negative. So as the sodium, so if you look at this little graph here, as the sodium starts to flow in, because it could be light that caused it, it could be touch, it could be pain, it could be pressure, something is opening the sodium channels. And as soon as those sodium channels start to open, the negative charge becomes less, okay, becomes more positive. So we see the voltage moving upward here. As soon as the voltage hits -50, and that is called threshold, approximately -50, depends on the neuron, that will fully throw open all the sodium channels in that area. And so the sodium channels open up fully. So as you see here, sodium channels open at -50. I guess we should say many sodium channels open at -50 millivolts. And at that point, there's so much sodium flooding in that the voltage will, there's no going back. You will get what is called an action potential. As soon as you hit that -50, an action potential will happen. So at threshold, that action potential will happen. And an action potential means we're just going to be moving electricity through the neuron. Will happen. Okay? So all the sodium channels open. The sodium floods in, because remember, there's a higher concentration on the outside than the inside. And here's, your phospholipid bilayer. So the channel opens, in floods the sodium, and the negative charge continues to get more and more positive because we're adding positive to that -70 with all those positive ions flowing in. And once it hits about 50, 40, it depends on the actual neuron, then that will cause the sodium gates to slam shut. So as soon as it hits that point, sodium gates inactivate. So here it's at +40. Okay, and the sodium gates just shut, so no sodium can get in and cause the charge to go even higher. And that voltage of +40 in this case will slam shut the sodium and open up the potassium channels. So now, because we have a higher concentration of potassium on the inside, it will cause the potassium to, this is just going from high to low concentration, no energy is needed. The potassium will just flow from high concentration to low concentration out. And again, if we look and see what happens when we slam shut the sodium gates and open up the potassium gates, we're going to see that now positive charge is now going to leave the neuron, and it's going to become more and more negative, okay? Because we're losing all those positively charged potassiums to the outside of the cell. And then it's going to dip a little lower than when it even started, so a little lower than negative 70. And that's called hyperpolarization. So it over polarizes. Remember, we're trying to get back to negative 70 here, and we actually went below. So it hyperpolarizes to negative 70. So the membrane repolarizes. And then we have this sort of resting where it kind of, it's called the refractory period. It's going to go back to that exact negative 70 again. But we have to think about how it's going to go back to the way it started, because now we have reversed our ions. If you think about it, we've taken the sodium from the outside, flooded it in, slammed that gate shut, that channel shut, opened the potassium channels, and flooded the potassium back out. So if you think, what has to happen during this refractory period? We need to get the sodium and the potassium back to the ratio it was before we conducted electricity through this part of the neuron. We need to get the sodium back out and the potassium back in, so the cell is sitting at negative 70 and the sodium's on the outside and the potassium's on the inside like we started. Because even though we've changed the voltage back to the negative 70, our potassium and our sodium is reversed. So during this refractory period, we want to get things back to normal again. And so that's where the sodium-potassium ATP pump comes in. It takes energy. It takes energy to conduct electricity, people. It takes energy. So we need to get the sodium back out because it's now inside the cell. We need to get the potassium back in and restore the original balance. And to do this, we use a pump, which is different from a channel. A channel works by following the concentration gradient, right? We open the channels, it's just going to, the ions will follow their concentration gradient from high to low, no energy is needed. The pump is working against a concentration gradient, so that one requires energy, but it is required to bring things back into the original balance, how we started, okay? So this seems like, okay, so now we're back to the negatives. If we look back at our chart here, we're back to the negative 70. The neuron is back at its resting potential, ready to go again should it need to. And it seems like a lot has happened here in this to conduct the electricity through this one section of a neuron. Okay, we needed to open sodium channels, close sodium channels, open potassium channels, and then close them, and then use a pump to return everything to balance. And this should take forever. How are we conducting electricity so quickly? Because the whole process does not take that long. That whole process takes 5 to 7 thousandths of a second, okay? And that is called an action potential. It's conducting electricity through your neurons. And action potentials are how we conduct electricity, right? We need to open sodium channels, change voltage, get the voltage back, okay? So if we look at this, I just showed you how one little section of an axon depolarizes and repolarizes itself. So if we look at repolarized here, what has happened is, okay, so we must have depolarized, which means sodium channels opened, we got to threshold, we went up, sodium channels closed, potassium channels opened, we hyperpolarized, and then we got back to normal. So we had one action potential happen here, okay? We need the action potentials to continue all the way down this neuron, all the way to the axon terminals, right to the end. So how does the next section undergo an action potential? Well, if we remember, we opened sodium channels initially and we flooded this with sodium, okay? So we changed the voltage in this section, okay? By changing the voltage in this section, it's going to start opening sodium channels as we move further and further down this neuron. So the electrical disturbance that happened right at the beginning of the sensory neuron, right where the light hit, the pressure was applied, the pain was applied. It opened sodium channels, changed the electrical charge inside this section of the neuron, which will cause sodium channels to open in the next section and cause another action potential, and then another action, and on, all the way down the neuron. Okay, and this is just another little picture of showing the gates. Hopefully you understand. Step 1, sodium gates open, in goes the sodium. I have this little game, this little simulation we do with this. It really doesn't apply online, as so many things don't. The potassium gates open, out goes the potassium, and then the pumps return the sodium back out and the potassium back in, and we can, simulate this with a little activity in class, but we cannot do it now. Just some information for you. How fast does this happen? Well, reflex signals, so we were talking about that reflex arc. We can conduct electricity through those 3 neurons, right? We've got the sensory, the interneuron, and the motor neuron. It's that simple little loop for a reflex. They go quite fast, 250 miles per hour. Okay, that's quick. Thought signals, 70 miles per hour. And then pain, 3 miles per hour. Why is the pain so slow? The pain is slower than the thought, so it gives us time to react, either through reflexes or thoughts. We can react to what's causing us pain and, hopefully stop what's causing us pain. So it just allows us time to react before we're immobilized by pain. But when we look at how fast these signals move, it's still really fast considering all that has to happen to make an action potential work.